So today we are going to do something, to be honest, a little bit depressing. I'm sorry. After you've all had a nice long weekend, we're going to launch into something that isn't terribly good news, but there are very positive aspects of thinking about what we have done to the atmosphere, what we are continuing to do to the atmosphere. And really, today sets the stage for the rest of the quarter, because for the rest of this week, for the rest of next week, we're going to talk about climate change. And that really is related to what we are doing to our atmospheric composition, and a number of other things as well that we'll take a look at. But really, this is sort of the introduction. Today we're going to look at some of the other pretty nasty stuff that we're doing to our atmosphere and what actions we've taken to address those. We're also going to have a little bit of an introduction, if we get there, we might not get there, to Earth's climates. So who recognizes this sort of image? Everybody, right? Whenever we look up towards LA, especially in the summer when it's been dry for a while, it looks a bit like this. And if you looked at the air at where we are from LA, that's what we look like as well. Okay, so really of all of the lectures, all of them have some relevance to you because you live in the world, you live in the atmosphere, we experience at least some aspects of weather. But this is something that actually impacts you every second of every day because we breathe. We all like to breathe. It's quite important for us. And so this is the sort of stuff that we're breathing in. So it's important that we know about it, that we have a chance to think about it. So as a quick outline, we're going to go through a couple of quiz questions that seem to catch a fair few people out. But then we'll really start talking about pollution. And we're going to approach it in two ways. We're going to first look at air pollution by matter, by elements, by things like carbon, nitrogen, sort of stuff, basically. And then we're also going to look at atmospheric pollution by energy. And that's not something that we necessarily associate with pollution. But if we move around energy, if we move around heat, that is also a type of pollution. Okay, so we'll talk a little bit about that too. And then lastly, if we get to it, we'll talk about our introduction to Earth's different climate zones. So first of all, let's take a look at a couple of the tricky quiz questions that caught you out. But in general, it was a very good quiz this week, I thought. So let's have a look at Cyclone Yasi from 2011. This is a really cool shot. And so the question I asked you, was where will the storm surge be worse? Will it be to the north of that cyclone, which is just another word for hurricane, or will it be the southern side of that? Okay? And so I said that the cyclone is moving towards the coast in this way, so it was just about to make landfall in Australia. And so what hemisphere are we in? Southern. So if this is a central low system, which way are the winds moving around it? You can usually see from the clouds, right? You can see that wind is spiraling inwards and to the left. Okay, so those winds spiral into the middle. Okay, so if you think about what those winds are doing, they're moving like this. Okay, so on this side of our cyclone, which way are the winds moving? Are they moving towards land or away from land? They're moving away from land, right? Remember our winds circulating like this? So it's actually moving away from land. We're still going to get a storm surge, but it's not going to be as large as down here, because on here, those winds are moving towards land. That wind is driving that water ahead. And so both sides will experience some storm surge, but the worst of it will be to the south here. Okay? And we did the same thing when we looked at Hurricane Katrina. So that one is sorted. Storm surge, definitely. Strong winds are not something to be laughed at, but definitely the storm surge would be what you should be most concerned about. The other one, I told you that this is one of my favorite questions, and you saw that we actually formed a hurricane this weekend. It's very good timing. They always start to happen a bit worryingly. Whenever I talk about hurricanes, we get one. And so we formed our first hurricane of the season in the Eastern Pacific, Hurricane Amanda. Those of you who are following the Facebook group saw I posted a couple of times, because I showed you that little pocket that said it could develop over the weekend. It actually developed into a hurricane on Friday, much, much faster than thought, and it actually hit Category 4. It was 1 mile an hour short of being a Category 5. And that's actually pretty amazing. We don't usually get our first hurricane of that size in the Eastern Pacific until mid-July. So it's very unusual that it happened pretty early on. And the reason that it's dying right now, the reason that we're not concerned, is that as it's turning towards the coast of Mexico, it's encountering this strong wind shear, these winds in the upper atmosphere which are moving in different directions and basically blow that nice sort of structure of the hurricane apart. So instead of having this nice central area with this huge focus where a lot of that latent heat energy is being released, instead those winds are blowing that air apart and the latent heat is being released in a larger area, and so it doesn't fuel that system as much. So strong wind shear is not a good thing if you want to build a big giant hurricane, whereas we really need it in order to form severe thunderstorms and tornadoes. This one, the trick here is to look for the hook. Okay, so also look at the scale. You can see individual towns marked on the map here, and you can see that there's this hook to the radar image, and that's really quite indicative of a supercell storm. The supercells tend to have this little hook to them, and remember that they're very powerful, but they tend to be smaller. This is actually our mesoscale convective complex, and you can see that these outlines here are of entire states. This is one of the Great Lakes. Okay, so it's a very different scale of this system. And then lastly, the one that people really didn't like was this one. Okay, so you measure air pressure over several hours and see that air pressure is gradually rising. So is the hurricane coming towards you or moving away from you? So let's first of all think about rain, because rain is easier to think about. If the hurricane is coming towards you, is it going to start raining more or less? More, right? Until you hit that eye and then the rain will stop. It's going to become more intense as it moves towards you. Okay. Is the center of our hurricane a low pressure area or a high pressure area? It's low. So if it's moving towards you, do you think the pressure is going to be falling or rising? It's going to be falling. If that low pressure is moving towards you, the pressure that you measure at your location is going to get lower and lower and lower, and then it's going to be lowest when that hurricane is right above you, and then as it moves away, you're moving away from that central low pressure, and so it's going to be rising. Okay, so in this case, that hurricane was moving away. So one of the other ways of thinking about this is, if you imagine that you are standing in one spot, okay, and then this graph sort of moved sideways over the top of you, so you'd experience, first of all, a little bit of rain, and then a lot more rain, and then a huge amount of rain, and then nothing in the middle. Huge amount of rain again, a little bit of rain. And so that's what you would experience as that hurricane moved across you. And here, if you imagine the same thing, if you were stood here, you would be measuring high pressure, and as that hurricane moved past, you would be getting lower and lower and lower, and then a central, really low pressure, and then as it moved away over the top of you and beyond, then you would start raising your pressure again. So hopefully that will help for anyone who got a bit confused by those questions. And if not, then please take the opportunity to ask your TAs in discussion. I'm sure they'd be happy to help. So, what is pollution? We use that word all the time, but we don't necessarily have a definition for it readily accessible in our head. So for this purpose, for our class purposes, we're going to say that pollution is anthropogenic. Everyone's heard of anthropology, which is the study of humans, right? So anthropogenic is just human-caused. That's what anthropogenic means. Redistribution of matter or energy. Okay? So we're just moving energy or matter around due to human activities, due to our presence. Okay? So that's what we're going to call pollution for this class. So let's think about matter, first of all. So we're just dealing with stuff. Actual physical things with mass that we put into the atmosphere. And we can break these down into two types. We can break them down into primary pollutants. So these are things that we emit and go straight into the atmosphere. So things in that sort of primary pollutants cloud on the left there, you can see are things like nitrous oxide, carbon dioxide, carbon monoxide, pretty nasty stuff. But then we also have secondary pollutants. So secondary pollutants are chemical reactions that create new things using those primary pollutants. So first of all, we emit our primary pollutants, but when those primary pollutants are in our atmosphere, they react to form something new, okay? And so one thing that happens is sometimes we react things like nitrous oxide or sulfur dioxide, we react those with water and we create pretty nasty acids, okay? Things like sulfuric acid, nitric acid. So those are examples of secondary pollutants. We don't emit sulfuric acid, but it can form in the atmosphere as a result of combinations of water and nasty sulfur gases, okay? So if we think about our primary pollutants, then there's a number of different sources for those, and some of them are, I don't want to use the word natural, there are natural sources of those gases to the atmosphere. They don't really fall into the category of pollution because it's not anthropogenic. But we do have things like volcanoes give out pretty nasty sulfur gases. If you've ever visited a volcano, it sometimes smells of rotten eggs. That's really nasty sulfur gases coming out of there. They also emit CO2. Those are natural sources of those gases to the atmosphere. But we also produce a certain amount of these pollutants, and they can be from stationary sources, so things like big power stations, big sort of chemical plants. But they can also be moving sources, things like cars, aeroplanes. So we have a number of different sources for these. So I'm actually going to make you talk to me today. I'm not going to let you escape, okay? It's 2 weeks to go. You can do this. So I want you to think of two things. Hopefully you have a friendly-ish neighbor, so you can turn to them, okay? If not, I'll wander around. You can tell me. So I want you to tell me what makes air pollution different from, say, water or ground pollution. What makes air pollution different? So see if you can come up with at least one thing for that. And what challenges are there that we face in addressing air pollution specifically? And what you'll find is probably the challenges you come up with will be related to what you came up with for the first question. Okay? So turn your brain on for today and talk to your neighbor. Give you 2 or 3 minutes to come up with one thing for each. Okay, well I had some very good suggestions from this side, so I'll give you guys a chance to help me out. So does someone want to tell me what makes air pollution a little bit different from, say, ground pollution or water pollution? Yeah?
Air pollution spreads a lot faster than the air.
Absolutely, it spreads out. It doesn't matter if it's being released in one place, it's going to mix into the atmosphere. So it's not just one person's problem. If you're polluting a river, that's your problem, it's local. The problem with air pollution is once we release it into the atmosphere, it mixes, and so it becomes everyone's problem. So that's a really good one. Anyone else? Being so shy. So tell me your one, because you had a really good one.
Air pollution is easier to get into human body.
Yeah, we breathe it in, right? It's different from the sort of water or ground pollution. Those we can probably take steps to avoid. We can't stop breathing. It is pretty unavoidable. We can choose perhaps not to drink polluted water. We're in a place where we're fortunate enough to do that. But we can't necessarily choose not to breathe in polluted air. Short of carrying around gas cylinders, that's not going to work for us. Okay, so again, it's going to affect us very, very deeply. Anything else? How about challenges? What challenges do you think there are in addressing air pollution? Come on, it's 300 very smart people in the room. I'm sure you can give me at least one challenge. Absolutely. At least some of these pollutants are pretty vital to our lifestyle, right? Things like CO2. If we're going to try and reduce CO2, that's going to take a significant impact on our lifestyle, on things like the price of power. And so our economy runs on this stuff. It's going to be difficult to switch away. Anything else? Yeah.
I just say that the industries are not regulated, like they don't have like corporations, they just pollute and they don't repair the damage they do.
So there are certainly, regulation is a challenge. Sort of how do we enforce that? How do we measure it? How do we know it's that place rather than another? Definitely is a challenge, and we're getting better at doing that in the US, but not everywhere. What about politically? What are we going to need in order to address serious air pollution? What do we often need? Global cooperation. We're not going to need just us to decide one thing. We're actually going to need an awful lot of people around the world to agree to this. And we managed to do that. Can anyone know which gas we managed to control with international cooperation? CFCs, absolutely, which were destroying ozone. There was a direct human consequence of that, and we managed to create worldwide cooperation and deal with that. It's going to be more of a challenge with some of these others because of this economic power struggle that's going on, but it's a really interesting question. So I just wanted to get you guys thinking about this. Think about this. Air pollution isn't limited by political boundaries, geographic boundaries. It travels. And everyone has to deal with it. It's not something you can opt out of or pretend isn't there. So think about those as we talk about the rest of today. So let's talk about some different types of air pollution. And I'm afraid this is a bit of a list, but these are really the important ones that we care about. And mainly we care about them because they affect our health quite seriously. So the first is aerosols. And you remember hearing that word right back, I think in lecture 1 now, or even lecture 2. And we call this sort of particulate matter. It's basically little pieces of liquid or little pieces of solid that are really, really, really tiny and so float around in the atmosphere. Okay? And so we will inevitably breathe those in. And so these can be removed. They can be removed just if the air gets still enough. Some of those will settle out. You can also sort of basically wash them out of the air with sort of rain. So you know that on nice days after it's been raining in LA, the air looks a lot clearer. That rain has carried away some of the nasty stuff in the atmosphere. And you can see some good examples in the left-hand diagram, at least, of who's been on a freeway and seen something like this. Most people, right? And you go, oh, and you hold your breath for that minute as you go past, like that's going to make any difference. So yeah, we have things like that. There's sort of soot in the atmosphere all the time. Other things are things like lead. And you guys are all way too young now to remember that you used to have leaded gas. You used to have leaded versus unleaded. And you got into quite a lot of trouble if you put the wrong one in because it destroyed your engine. When I was a kid, it was like that. So, and the other thing is dust. And this is one that affects us in California quite specifically. And so I wanted to show you a little bit of our dust problem. So, hopefully you know that we are not somewhere that has a lot of water. We have to bring in a lot of our water to Orange County and LA and surrounding areas in San Diego. And so here's a little map showing the California aqueducts. And in particular, I want to draw your attention to the Los Angeles aqueduct that runs up into the Eastern Sierra. So this one here that runs up through into the Eastern Sierra, goes past Owens Lake, and it goes up to Mono Lake for anyone that has visited. And the nice thing about this aqueduct is it goes downhill all the way. We don't actually have to pump that water. And so these very clever guys at the turn of the last century realized this, and it's a fascinating story for any history people, the history of the Los Angeles aqueduct, because these guys basically secretly bought up land around here, and it sort of caused a small little civil war in California for a while. But has anyone ever driven past Owens Lake? No? Well, you might not have noticed, because it doesn't look like that anymore. It looks like that, okay? Because all of the water that was flowing off those mountains and into that lake was diverted into the aqueduct and sent down to Los Angeles, okay? Which is nice in theory. It provides us with more water. Wasn't great for the local farmers, for the people that depended on that, but that's what happened. But the problem we have now is the dust that comes off the bottom of that lake. You can see most of it is dry, and at the bottom of that dry lake bed, it has really, really fine dust, and that contains some sort of pretty nasty metals that we don't necessarily want to have in our bodies. And when I talk about dust, I don't mean the stuff that you can see necessarily in the air. When we're talking about the really harmful particulate matter in our atmosphere, we're talking about really tiny things. So on the diagram on the left, you can see this is an average human hair. And you can see that particulate matter 10, which is 10 microns, so 10 millionths of a meter, which is tiny, they would fit maybe about 5 of them across a human hair. If we talk about particulate matter 2.5, which is 2.5 microns, that's even smaller, that's 2.5 millionths of a meter. You could get 4 of those across each of the PM10. And the reason that this stuff is so nasty is because it can make it into your lungs, and it can make it a long way into your lungs. It basically lodges itself in the little alveoli in your lungs, and it's very, very difficult to get rid of that dust. All of the hairs and sort of things in your lungs that help do that don't really stretch that far in. And the PM2.5 is small enough that sometimes that can even cross from your lungs into the blood itself and be carried around into your system. And so we don't want there to be lots of dust in the atmosphere that we're breathing in that's going to affect our lung capacity, okay? And Owens Lake, which dried up because all that water was diverted to LA early in the last century, is now the largest single source of dust in the US. When the winds get going, all of that really fine material off that lake picks up and enters the atmosphere, and it's a huge issue for residents in that area, okay? And if you live in LA, how much of your average water bill do you think goes to limit the dust coming off that lake? So we're trying to take actions to try and stop the dust coming off. How much of your water bill do you think is spent on that? Okay, let's see how many of you know where your water bill goes. It's a bit of a spread. The most pessimistic people would be right. If you voted D, you were correct. 15% of the average water bill in LA goes to trying to stop the dust coming off that one lake. Isn't that amazing? And the reason for that is it's really quite challenging to do. So you can see that right now, what they do to try and address this is they flood the bottom of that lake, and that stops that dust entering the atmosphere. But that's a lot of water that we could use. It could basically sort of supply San Francisco for a year if we use that water for LA instead. And that's really not something that we can afford to do down here where we're so water limited. And so they've tried putting gravel across the top. They've tried sort of putting grasses and things like that, but they have to be really tolerant of salt, because as that lake dried out, all of the salt get left behind. So it's a really interesting problem and question if you want to do some more research. Okay, so one last thing. So that's Owens Lake. Can anyone think of another very large area of water that we are a little bit worried about drying out because we are diverting more and more water away? Well, the Colorado River has its own problems, definitely, but somewhere else close by. Yeah.
Is that the Salton Sea?
The Salton Sea. Who's been to the Salton Sea? Not that many people, because it doesn't smell that good quite often, right? Anyone that remembers that? See that down there in the Coachella Valley, the Salton Sea? Right now, we're pumping quite a lot of water into that to maintain it at its current level. We created that completely by accident. It's not a natural formation, by the way. We accidentally flooded the Colorado River when they were trying to create irrigation channels. And that river flooded into the desert for 2 years and created the Salton Sea. And it's been drying up ever since. And we're diverting more and more water away. And so we're really concerned about the dust that could come off there. That would affect everyone around here. And in particular, because there's a lot of farmland, we've got a lot of pesticides, pretty nasty metals in the dust at the bottom of that lake. So anyway, I'm getting distracted. Second thing that we are concerned about, carbon dioxide and carbon monoxide. So you've seen this graph before, the Keeling curve, showing how CO2 in our atmosphere is increasing through time. And obviously, this forms the basis of really the rest of our lectures this quarter, so I'm not going to dwell on that. But carbon monoxide, most people have heard of carbon monoxide. Who has a carbon monoxide detector in their house? Yeah, a lot of people, right? Especially if you have a gas boiler. Carbon monoxide is produced when you have incomplete combustion. If there's not enough oxygen in the air, instead of producing CO2, we get CO, carbon monoxide. And it's very, very dangerous for us. And that's why we have detectors in our house that can catch that. So my question for you now is, carbon dioxide and carbon monoxide are emitted by burning fossil fuels, for example in your cars, and by burning vegetation. So are they primary pollutants or secondary pollutants, do you think? So 73% of people agree with me that they are primary pollutants. You're right. They're what we're putting directly into the atmosphere. If then they react in the atmosphere with something else, then they would be secondary. Great. We're on track. The second thing, or third thing rather, that we emit are sulfur gases, so in the form of sulfur dioxide, and then SO3 as well. And these are pretty nasty. They can cause respiratory problems, so they can cause trouble breathing for certain populations of people. And the other thing that they cause is acid rain. So do you remember I said that these gases can react with H2O in the atmosphere to produce sulfuric acid, which is H2SO4. It's a really strong acid. You don't want to get that on you. And it's actually had a huge effect on some of the lake ecosystems up in Canada, in Scandinavia in particular. And do you remember I said that air pollution doesn't stay where it's put. It doesn't care about political boundaries. And acid rain is one of those issues where that really came to light. Because look, where is the worst acidic rain in the US? East Coast. Which way is all of the air pollution that we produce here going? That way. Do you remember all of our weather systems move from the west to the east, and so a lot of the emissions that we put into the atmosphere head their way. And so definitely they also have emissions of their own, but they're also inheriting the air pollution that we emit as well. And that was the same for Scandinavia, and really the UK, England. We burnt a lot of coal, put a lot of sulfur into the atmosphere, and it didn't affect us. It affected Norway, Sweden, which were downwind of us. Okay? So this is a real problem. And definitely in some places those lakes have become too acidic to have fish, so they can really strongly affect ecosystems. And if you've ever seen a film set in London in the 19th century, something like Jack the Ripper or Sherlock Holmes, then often they have these swirling fogs, right? And that's because we have these sort of very London sort of smog events, where we really did have pretty nasty air pollution in the 1800s and early 1900s. And that was because we were burning a lot of coal in houses and elsewhere. And now we're starting to see the same thing in China, where they also have a huge amount of coal and they're starting to burn it in homes. And they're also encountering some of these problems where we put SO2 into the atmosphere, we combine it with H2O, and we produce this nasty sulfuric acid, and it really takes its toll on people's health. So this is our London-type smog, which is completely different from LA-type smog. I've just been moving from one to the other. Okay. So 4, 5, and 6, I'll put up together because they are all related. So we have nitrogen oxides. We sometimes call these NOx. The X at the end stands for, it could be 2, 3, or just 1 oxygen. And these again cause respiratory problems. They're not terribly good for our lungs. Things like volatile organic compounds. This is stuff like that you would smell from a gas can or something, that sort of nasty organic smell. Things like methane and butane. And then we have photochemical smog, and this is LA's type of smog. Okay? And photochemical smog has pretty nasty stuff in it. We have things like ozone, peroxyl nitrate, formaldehyde, pretty nasty stuff that we end up breathing in. So let's look at why the photochemical smog is different. And it's different because instead of needing water droplets in the atmosphere like our London-type fog, in LA, we just need sunlight. It's where the photo bit comes in. So it's very dry air, and then we take those volatile organic compounds, and we take our nitrogen oxides and we combine them with sunlight, and we get these really nasty compounds that happen as a result. So is our photochemical smog, is it primary pollutant or secondary pollutant? Secondary. It's forming as a result of additional reactions in the atmosphere. Okay. So, obviously we care about these things. We don't want them in large amounts in our atmosphere. So who is in charge of this? And what do we actually look after? So we have what we call criteria pollutants. These are the big 6 that we measure sort of every day, almost every hour in different places to try and keep track of how our atmosphere is doing. So things like those nitrogen oxides, ozone, carbon monoxide, sulfur oxides, lead, and particulate matter, those are the things that we measure and have to keep under a certain level defined by the EPA, which is the Environmental Protection Agency in the US. Okay, so that's our 6. And then we have hazardous air pollutants. Those. Okay? So we're constantly monitoring a lot of different things. There are a lot of harmful things that get released into our atmosphere. These are there in less quantity, but we still care about them, so we still measure them. So don't panic about these. But you can see that things like pesticides, herbicides, other nasty organic type chemicals. Okay. So what isn't on that list of criteria pollutants that you've heard about a lot? Thinking back. What does the Keeling's curve show us? What gas is that looking at? CO2, carbon dioxide. It's not one of our criteria pollutants. And there's actually been quite a battle about assigning that to our, where is my slide on that? I jumped ahead. About CO2. It's actually taken a long time to describe CO2 as a pollutant. And in 2009, we had what we call an endangerment finding, and this was a huge step forward in being able to regulate CO2. Because before that, it wasn't defined as harmful, and so there was no sort of power to regulate it. And so the Environmental Protection Agency said that these 6 well-mixed greenhouse gases, which include CO2 and these other ones, in the atmosphere threaten the public health and welfare of current and future generations. And that was a really important ruling because from that point on, that allowed the EPA to try and impose regulations on the emissions of CO2. Okay? And that may be things like demanding more efficiency from your cars or affecting the emissions from some of the bigger stationary sources. But very many states did not like this. And so 14 states actually sued and said that this was not an appropriate thing and that the science behind climate change wasn't proven. But in 2012, the Supreme Court upheld that because there were also other states that said that this was something that we did need to do. So this was a very good thing for us, and I'm sure that more will come of that. So, what has our air quality been doing recently? If you speak to your parents, if they lived in LA in sort of 60s, 70s, then they'll be able to tell you that actually our air quality is doing a lot better than it was. It's finally a good luck story, okay? We may still have to contend with some of these nasty pollutants, but look, from 1975 to 1990, really all of those pollutants have been dropping in concentration. We've been reducing all of those in our atmosphere, and lead most spectacularly of all, mostly because we took it out of our gas, okay? And so you can see that we're doing a reasonably good job at controlling the amount of air pollution that's happening, even as we see greater and greater populations here. And that's because we have these regulations. We have the Clean Air Act, and we have amendments that were made shortly afterwards. And we therefore have certain laws that have been passed to improve air quality both in the US and also here. And unless you are reading quickly, as I skip through it, can anyone tell me, or turn to your neighbor and tell them one thing that affects you, that you know of, one law that is required of you in LA, at least, possibly elsewhere, that improves our air quality? So think about it. Smog check, which I have still failed to accidentally miss. Okay, anyone else? What else does your car have fitted to its exhaust, hopefully? The catalytic converters? Yep, heard of those? Has anyone noticed the big rubber sleeves they have on gas pumps? Those are basically to stop things like volatile organic compounds escaping out. So as that fuel is transferring between the pump and your car, this sleeve basically traps anything that would escape. And you wouldn't find those if you went to England. It's a very different system there. Okay? So all of these things have helped, at least in Orange County and LA, and also elsewhere, in controlling some of the things that have been contributing to our air pollution. So smog tests, things like cleaner gas, taking that lead out. There's rubber sleeves on gas novels, and most importantly, this ban on CFCs, which we keep talking about. So let's talk about us here in LA and Orange County. So every day, just the cars that we drive around emit 2 million kilograms, or 2,200 tons, of hydrocarbons into the atmosphere every day. And 1 million kilograms of nitrous oxides. And this is, you remember, those two things are important components of our photochemical smog. So it's not surprising that often our days look like this. But that's every day. And you know that the freeways are never empty, right? So why is it that smog is much worse on some days than others? What days is it when it's clear in LA? When will you know it will be clear? After it's rained. I think that's a good suggestion. So things like our atmospheric conditions itself affects how much of those pollutants stay where we are. Okay? So when do you think air pollution will be worst in LA? Okay? So think about the wind conditions and think about whether our air is stable or unstable. Okay? So when will we see the worst air pollution? Okay, let's take a look. I would agree with the majority, I think, in this case. So you can see dry is always something that we would like. When there's water in the, well, we don't want it actually. Dry is something which is as bad a thing because there's no water in the atmosphere, we're not scavenging particles out. Light winds, why did you say light winds? Someone that voted that. Yeah, it's not being blown away. That pollution is much more likely to stay where it's being emitted. Okay? So we're much more likely to have that pollution just sitting in LA. It's not going to be moved elsewhere. And then stable air. Is stable air the stuff that rises or the air that stays close to the ground? It stays close to the ground. So again, if we were to have unstable air and that air rising away from the surface, it would carry away that pollution. And so if we have stable air, that air is staying nice and close to the surface, and so we're going to get much more pollution. Okay, so these are the things that we think about. It's not just how much we emit and not when we emit it, but it's also the atmospheric conditions, the weather conditions that affect how much pollution we're likely to see. And so things like turbulence, low wind speeds, there's more concentrations, and also topography. So, for example, LA, we're surrounded by mountains on all sides, and that tends to keep our pollution closer down. We're also underneath our nice high pressure, so we tend to have stable air. The other place that really suffers from pollution is Denver. And again, it's surrounded by mountains, and all of that air sort of stays nice and stable over the city and collects pollution. So do you remember we talked about inversions? And I sort of said that when you see that line of nasty smog across the city and then nice blue, clear air above, then what we're seeing there is an inversion. And so this is what that diagram is showing you. It's showing you that at a certain point, up high in the atmosphere, the air is warmer. And so we create incredibly stable air. So up here we have nice descending warm air as part of our high pressure system. And that keeps sort of cooler air down here close to the surface. And especially if that inversion layer basically sort of blocks off any way that the wind can escape over the mountains, all of that sort of pollution that's emitted tends to hang around underneath that inversion layer, and that's what we're seeing. And that sea breeze also tends to move it inland, and that's why it's pretty miserable in the valleys inland and, say, riverside during these sort of times, because all of that air travels inland. And so how is our air pollution today? So here's a cool link, and you can go and find it if you want. You probably can guess by being outside that it's not great quality today. It's sort of pretty moderate. It was sort of good over the weekend, but we've been dropping. And certainly inland, it's already unhealthy for certain sensitive groups. And that's because we have this sort of dry, sunny conditions again. So you can keep an eye on how our air quality is doing. So now let's think about energy. So those are all ways that we pollute the atmosphere by matter. We're basically putting stuff into the atmosphere. Now we're going to think more about energy, okay? And this is because we as humans are changing the surface of the Earth. And if we change the surface of the Earth, we are going to affect the energy balance. This thing that we talked about way back when we talked about albedo and things like that. So we're going to come back to this idea of albedo, and we're also going to come back to this idea of sensible heat versus latent heat, okay? So how many people have heard of urban heat islands? Nobody? Okay, well, something new for everyone. So what happens with urban heat islands is that we get much warmer temperatures in the middle of a city than we do on the outskirts. And probably some of you might know, if you go to downtown LA, it feels really hot. And then as you return to Orange County, some of that might be just the weather throughout the day, but some of it is also due to the fact that it's a very built-up, urbanized environment. And so for all of you engineers in the room, then definitely this is something that you guys are helping us with a lot. So you can see that as we go from sort of rural into the middle of our city, in my diagram here, our temperature tends to go up, okay? So here's an example of Vancouver, which is a really cool city up sort of on the Pacific coast in Canada. And you can see that those lines here are not isobars this time, they're isotherms. They're connecting areas of equal temperature. And so I want you to have a look at that diagram and tell me, from the very middle of the city in downtown to the outskirts, what's the biggest temperature difference you can identify? Okay. So what's the biggest temperature difference you can find on that map going from the center of downtown to the outskirts? Okay, let's see how good we are today at adding. Reasonably good. Reasonably good. So someone tell me, where is the very hottest temperature? What's the hottest temperature that you can find on there? 27, and it's right in the middle of downtown, right? What about the lowest temperature? Where's the lowest temperature on my map? 18, and it's right down here, out sort of towards the outskirts of the city, right? Down here near Richmond, okay? So 27 minus 18 is 9. Hopefully everyone can do that in their head. Okay, so that's actually a huge difference. I know that you're not Celsius people, but that's a huge difference, okay? Just sort of for one day. So let's have a think about why we're seeing such a huge increase in our temperatures in the middle of a day, okay? And also at night we see this. Well, first of all, not so much here, we're sort of doing the reverse here, but especially in the winter, say in Chicago, in New York, what's the temperature like? It's really cold, really, really, really cold, okay? And so we use energy to warm us up. Is your house perfectly efficient at keeping in that energy? No, most people's really aren't, okay? And this is what this diagram shows you. Do you remember we said that we can use infrared cameras to look at where energy is escaping? So where is energy escaping from this house? Where do you think? The windows, definitely, and we're probably aware of that. Where else? Up through the roof. And that's why insulating your roof, I know that you're all hot place people, but in cold places you insulate your roof because that's where a lot of that heat escapes, okay? And so where does that heat go? It's leaving your house. That doesn't mean it just vanishes. It's actually going out into the environment, and so that heat energy is going to warm up the environment. So first of all, we just get release of anthropogenic heat. Has anyone ever stood around some of these buildings where the output is from the air conditioning? No? Has anyone ever stood next to an air conditioning unit in full force? the outside bit? What does it feel like? Hot, yes? You don't, go and find one and stand next to it. And you'll find it's hot. So that heat isn't just being sort of magically vanishing, it's being released into the environment. And so that is one contribution to this heat island effect. The other one is that by building across the surface, we're affecting how much light is reflected away. Okay, we're coming back to our albedo idea. And so here you can imagine going from outside of the city, we have relatively flat, horizontal sort of fields or something like that, into the outskirts of the city where we have low buildings, into downtown where we have big skyscrapers. And I want you to look at what happens to the solar radiation as it arrives at each location. So let's think about it. Outside of the city, that energy arrives, it hits that horizontal surface. Some of that energy is absorbed by the surface, and a certain amount is reflected away. Okay? Incoming radiation here hits this building, certain amount of it is absorbed, and a certain amount is reflected away. But some of that reflected energy is then hits another building, where it's again, some of it is absorbed, some of it is reflected back. Okay? And if we think about really tall skyscrapers, again, that's the same thing. Some of that energy is absorbed on this side, and then some of that energy will bounce and be absorbed on this side, and this side, and this side. Okay? So, which of these is absorbing the most of the incoming energy? So every time it hits a surface, a certain amount of the energy is absorbed. So in which of these do we hit the most surfaces? The tall buildings, because every time it reflects off and hits another part of the building, a certain amount of that energy is absorbed. Okay? So, thinking both about this process, but also perhaps about what those buildings are made of. Okay? What do you think the presence of cities does to albedo? So talk to your neighbor for a second. So taking both into account this, but also what those buildings and what our surfaces are composed of in cities, what will they do to the albedo? So we have a 60-40 split, approximately. So the majority say that our albedo will decrease. So why did you say it would decrease? Yeah. Are you volunteering? Well, volunteer.
It's like reflecting, but then it's
Yeah, absolutely. If we think about this process, we're absorbing more of that incoming radiation and reflecting less. And so if we're absorbing more, reflecting less, we're going to have a lower albedo, and so that's going to make our temperature warmer, right? And that's certainly part of it. But what are skyscrapers made of? Glass? Yeah. What are a lot of the tall buildings around LA made of? Steel? Concrete? What color is the concrete? Gray, white. What is that going to do to the albedo if we have lots of nice glass white surfaces? It would increase, right? So actually, it's a bit more of a challenge than we're thinking. Albedo is not something that's really simple to think about, because definitely when we have tall buildings, we're absorbing more of that radiation. But remember, they're often really reflective surfaces, okay? And so that's something to think about. It sort of depends. So concrete, lots of those really white reflective surfaces are going to reflect more incoming radiation, okay? And that would increase albedo. But when you have tall buildings, and perhaps if you have a parking lot like outside where we have that asphalt which is nasty and black and really absorbent. So these are things that you want to think about, because cities have identified that it is a problem. This urban heat island effect is a problem. And by thinking about things like this, we can start trying to address it. Okay, so the last thing, has anyone heard of green roofs? Yes? You've seen very many? There's not that many around still, but it's starting to be more of a thing, something like this. And it's not just because someone wanted a cool garden on top of a skyscraper. There's actually a real purpose behind this. And we're coming back to our idea of sensible heat versus latent heat. Okay? So, if you imagine the concrete outside during the day and then a patch of grass, which one will be cooler to walk across during a really hot day? Was it the concrete or the patch of grass? The grass, okay? And why is that? It's because of latent heat, okay? Because if you imagine the concrete, we have a certain amount of energy coming in, hitting that concrete. All of that energy that's absorbed goes into increasing the temperature of that concrete, okay? You think about what's happening to the grass surface. We've got both the grass and the soil underneath. The same amount of energy comes in, it hits that grass, it hits the soil. What's going to happen to some of the water that's in the grass and the soil? It's going to evaporate. And does that absorb or release energy? Absorbs, right? Okay? And so is the temperature of that grass going to go up as much? No, because a certain amount of that incoming energy, instead of increasing the temperature of the grass, goes into evaporating water from the soil and from the leaves. Does that make sense? Yes, sort of? So if we have green roofs, this means that, again, instead of all of that energy coming down, hitting that surface and being absorbed, instead, a certain amount of that incoming energy is going into the evaporation of water, and so the top of that surface doesn't increase in temperature as much. Okay? And so certainly in most cities, what we've seen is that as we've paved over places, as there's less soil, as there's less grassland, then we've seen an increase in the amount of sensible heat flux compared to latent heat flux. Much more of that energy coming in goes into increasing the surface temperature. Okay, because there's less water in the surface to evaporate. And so we see higher and higher temperatures in the center of the city. And so this is a pretty serious idea, the idea of these green roofs that could help address some of that increase in temperature. Okay, so the fundamental bottom line is that all of these three ways, by changing the albedo, by releasing heat that we've been using for comfort, and by changing the amount of latent heat versus sensible heat that's happening at the surface, our total heat island effect can be anything up to 22 degrees Fahrenheit. That's the difference between like 90 in sort of middle of LA and, I don't know, 70 or so out in the suburbs. And so that's really pretty substantial. And the bigger your city is, unsurprisingly, the bigger that heat island effect is. So in LA, you can imagine it's probably a pretty substantial effect. So you can see that this is a log plot. So at the bottom you have population. It goes sort of 1,000, 10,000, or something like that, 100,000, okay? And you can see that there's a bigger and bigger temperature difference between the urban, the U there, compared to the rural, okay? So there's a bigger and bigger temperature difference as you get a bigger city. And this is just a reminder that we may think that we're sort of small and the Earth is huge and we're not having a big effect, but all you need to do is look from satellites in night, and I think this is a beautiful image, showing just how much energy, remember light is energy, that we are releasing at times into the environment. And you can see from that where a lot of those urban heat islands are going to be where those urban areas are. And yes, there are large areas that aren't affected, but there are also significant areas that are. So, here's a question for you. Do you think that the urban heat island effect will be constant through time? So I just showed you that graph, right? So tell me, do you think the urban heat island effect will be constant through time? And if not, what are the various factors that could affect it? So 80% of people were listening, and no is the right answer. Okay, it's not constant through time. So tell me, why is it not constant through time? What will change through time? Population. I just showed you the graph, right? So population is the easiest one. And what do you think has been happening to our urban populations through time? Increasing. Just we have more population in general, but also in a large part of the world, the drain is from from rural areas into big cities. Okay. Any other things? No? Okay, I'll let you off. So, this has actually created a bit of a problem. The fact that this urban heat island exists, okay, is a problem in itself, but it's also created a problem when we're looking at climate change. Because where do you think most of our big, long temperature records exist? Are they in the middle of Arctic Canada? Where are our really long instrumental temperature records likely to be based from? Cities, okay? So if you imagine, say, in London or around London, we have instrumental records that go back maybe 200, 250 years. It's because there were people there were people measuring those temperatures. And that's a problem because through time, if we imagine taking a temperature record from London, we might see that there's been an increase in temperature. But what else has been happening in the last 250 years in London? More people. There's just a whole bunch more people. And so how much of that change that we're seeing in that long-term record is actual climate change and temperature changing? How much of it is actually an urban heat island effect? And this is a real challenge, and a big part of trying to identify and look at these long-term records is trying to find ways of teasing out those two effects and trying to find areas that aren't as affected by these urban heat island problems, okay? And so that has created a small issue for us there. So, we have got time after all, so we're now going to have a little bit of a quick introduction to climate. That's going to form the basis of the rest of our lectures for this quarter. So, this is a blast from the past, but hopefully you remember that weather is the state of the atmosphere at a given time in a given place. And remember, we had 5 things that we talked about, and we spent a lecture on each of these really, on temperature, air pressure, humidity, how much moisture there is in the air, cloudiness, and wind speed and direction. Those are the 5 things that categorize our weather at a particular time. When we talk about climate, we talk about the average of those. We don't care if there was a giant hurricane yesterday or if it's going to rain on July 4th, which would be really weird in LA. What we care about is the average. On the average in July, what is the temperature? Okay? And that's the problem in saying that this winter was due to climate change or that particular hurricane was due to climate change. We're looking at long-term averages. Okay? So, tell me, what is the climate in this particular location? Where is this, by the way? Joshua Tree. What is the climate like in Joshua Tree? Hot. I go with hot. What else? Dry. What is my picture of? Snow. Is that climate or weather? It's weather, okay. So, but you could still address that you still knew where it was and you knew that the average temperature was hot and dry. Okay? Because it usually looks like that. If you haven't been, you should. It's only an hour and a bit away. Okay. What is the climate like here? Is it hot or cold? Hot? Is it wet or dry? Wet. What is the climate like here? Is it hot or cold? Is it wet or dry? Slightly more difficult to do, right? So how do you know? The trees, okay? The vegetation, right? This is one of the advantages of living in the real world, okay? Which you have done for at least 18 to 20 years, okay? So you know this stuff. And what you can do is you can identify what the climate is like by looking at the vegetation. And so when we started thinking about ways of classifying the different climate zones on Earth, this was one of the ways we did it, okay? In particular, Mr. Kirpin, he came up with this system which distinguishes different climate zones from each other based on the type of vegetation you get. And he described an awful lot that I don't want you to waste your time memorizing, okay? Please don't do that. But what I would like you to be aware of is those main 6, okay? So our main 6 are tropical, dry, mild mid-latitude, severe mid-latitude, polar, and highland climate zones, okay? Those are those big 6 categories, okay? And then you can see that it is broken down further, say, based on whether you have a dry season, whether summer is dry or winter is dry. These sorts of things will sort of subdivide those, okay? But what I would like you also to be able to do is look at this sort of map and start explaining why we see those different climate zones where we do, okay? So I'm going to give you a few minutes now, and I want you to really look at this map. Look at where the tropical zones are. Look at where the dry climates are. Think about where the highland ones, the polar ones, they're a bit more obvious. Think about what mild mid-latitude means compared to severe mid-latitude. And I also want you to think at the same time that you're looking at that about the 3-cell conceptual model. It's coming back again. Because obviously those bands that we saw in the 3-cell conceptual model are also going to influence the type of vegetation we see. Okay? And some of you saw that in discussion already. So I want you to take a good 5 minutes. And in particular, I want you to think about the dry climates, okay? So look at where the dry climates are and see if you can explain why they are where they are, okay? And the TAs will get up and wander around and help with this as well. Okay, everyone, hopefully you've had a chance to look at that diagram because there's an awful lot of information to take in. So I'm going to start with the easiest question. Where are my tropical climates found? Near the equator. Why are they found there? It's hot. And what does hot air do? Rises. And what does it do as it rises? Expands, cools, forms clouds. Absolutely. Okay, I'm glad that the brainwashing is working in some way. Okay, so what else do we have? Thinking about the other big features of our 3-cell conceptual model. What did we have at 30 degrees north and south? Remember we had that subtropical high? What sort of weather conditions were associated with that sinking air? Sunny skies, right? As that air comes down from the upper atmosphere, it's compressing, it's warming up. We're moving away from saturation. We have this lovely dry conditions. And where do you see the dry climates? Where are our dry climates? More or less 30 degrees north, 30 degrees south. You can see them running through Australia, through Africa. Is that the only place we get dry climates? Can anyone spot somewhere where we get very dry conditions that might not be associated only with air movement? So the poles are dry, but what type of climate would you call the poles? Polar. Okay, yes. What about in the center of Asia? What sort of climates do we see there? Dry. Why do you think we might have dry climates in the very center of Asia? It's downwind of the Himalayas, so we're in our rain shadow. It's also just a really long way from the coast and a long way from a source of moisture. Okay. So, and then you can see that mild mid-latitude, severe mid-latitude, what's the difference? Where do you tend to find those? Is there a pattern for those? I'm asking the question that probably suggests that there is a pattern for those. So can you find the pattern for those? Yeah, severe mid-latitudes tend to be higher latitudes. They tend to be more extreme. Okay, so last question of the day that you should know because I just told you the answer. So where are the tropical climates found? So tell me, where are the tropical climates found? Okay, let's take a look and see if we agree, which we hopefully do. Finally, we do agree. They are at the equator. So on Thursday, we're going to talk about past climate, so why climate changes and how we know it's changed.